Hello and welcome to the Robotics 2020 competition. This is a design video presentation of the UKMO team from Algeria. In this video we are going through the following outlines. First of all, introduction, then safety, rig mobility, mechanical design, BHA design, control scheme, main control algorithm, geo interface, trajectory simulation, and finally conclusion. According to the guidelines, the Group A task is to drill a wellbore to hit multiple targets at varying vertical depths and XY coordinates. In order to accomplish this task, the team have to design and build an autonomous physical miniature drilling rig, design a flexible and controllable bottom hole assembly mechanism, design a control algorithm with closed loop control of the rig based on downhole data, and finally design a human interface for data visualization and data handling. According to the guidelines, the targets will not require wellbore inclination in excess of 30 degrees from vertical, 15 degrees change in azimuth, or 10 inches displacement. Here is an example of the rock sample with two targets with different coordinates. After drilling the vertical phase, the device had to hit the target A then target B by adjusting the BHA.
One of the team's top priorities is making sure the entire operation is running complete safety and that no accidents occur during the competition. In order to do so, the team will follow the hierarchy of hazard controls, which can provide a framework for determining the most effective corrective actions to undertake. The hierarchy is a system used in the industry to minimize or eliminate exposure to hazards. These actions will range from wearing personal protective equipment to the elimination of the hazard or removing it completely.
In order to ensure the mobility of the rig was designed to be folded. Also, a specific wooden box was designed for the shipment. For the mechanical design, the horsing system is ensured by horsing servo motor connected to both screw set. On the other hand, the rotary system ensured by a pneumatic motor for rotation. The change of the azimuth is ensured thanks to the top drive servo motor. The directional BHA is basically composed from a sensor sub that contains the downhole sensor, an electrical knuckle joint responsible for the inclination angle, BHA stabilizer, and downhole air motor to rotate the drill bit. The electrical knuckle joint mechanism allows us to have various inclination and better build-up rate values.
The team's control scheme is presented below as a communication flowchart for the purpose of showing how MATLAB is planned to communicate with the motors and the sensors. For each motor, there will be either a servo drive or a variator that will feed all the information via Ethernet to the main hub. As for the sensors, we have the new IMHO downhole sensor, the load cell, and the flow meter, which will all be connected and controlled via the Arduino board. The Arduino board will then send all the information via Ethernet thanks to the shield accessory attached to it. The hub will then feed all this information to the MATLAB program where the data will be treated and plotted.
The main goal for the weight-on-bit controller is to eliminate the error between the chosen weight-on-bit set point and the measured weight-on-bit from the load cell. For the position controller, an error is calculated from the referenced and estimated position and fed to the PID, which after calculates a new system input. It is expected that this controller is going to be combined with the weight-on-bit controller. As for the three torque controllers, a set point RPM will be chosen and the set point torque will then be given as a result after the error is calculated from the chosen torque set point and then fed into the PID controller.
The graphic user interface for this year is made up of 6 sections. The first section contains gauges that show the most important information such as the warp, the ROP, the pressure, and the torque. The second section contains 3 graphs that will plot the warp, the torque, and the total depth, respectively, against time to see how they vary throughout the process. The third section is known as the magnetic surveying. This section shows how different directional parameters change, such as the world center coordinates, the longitude and the altitude, the true vertical depth, dogleg severity, northing and easting. The fourth section shows real-time variation of the build-up rate, the azimuth, inclination, and drill depth. The fifth section, which is next to it, shows the raw sensor data, which can change the yaw, the pitch, and the roll. The final section at the bottom left has the start and the stop button to control it.
These are the simulation results on a 2D and 3D plane the team has done on the theory of autonomous positioning. The method bases on the hypothesis that speed will be constant on the z-axis of the body frame and development position expression among the angle measurement with recurring equation. In simple words, it uses the last and current position to determine the next position. Results on the 2D plane of the XZ axis were satisfactory and the theory seemed pretty applicable in the process of deviating by creating a perfect curve.
This is a brief presentation of the main design features included and proposed in this year's edition. Further research and improvement will be done during the second phase to make the system robust with flexible and powerful mechanical components. Thank you for watching this video.